Gar. I'm presenting this work as part of my PhD from École Polytechnique in Montreal. My supervisors are Michel Desmarais, Amal Zouak, and our collaborator, Elizabeth Charles. And this is a data set of learner-sourced explanations from an online peer instruction environment. Our objectives are to introduce a novel source of data to the educational data mining community and use this as an opportunity to discuss, identify opportunities and challenges when it comes to learner sourcing. Learner sourcing is a term that's been gaining steam in research for the last little while. It's a variant of crowdsourcing, where you have students generate content that is used by their peers, but it's as an authentic part of their own learning experience. And we'll be looking at a place in our setting where not only are they creating that content, but they're curating it as well. For those who may know peer instruction, popularized by Eric Mazur, that's where we start. The idea is it's a very popular classroom practice where I will put up a multiple choice item on the board. My students will, via some kind of app or an audience response clicker system, they will vote as to what they think the correct answer is. I may show the distribution, but I won't reveal the correct answer. I'll ask the students to discuss amongst one another, try to convince each other of what the correct answer is. And then we'll ask them to re-vote. And we know that from experience and from research that this is a very interesting way to flip your classroom for active learning. And invariably, students move to the correct answer without a teacher intervention. So there's some magic happening in those mini discussions, which our research group tried to move into a technology-mediated version of peer instruction, what we call asynchronous peer instruction, which is what we're showing here. This is what it could look like. Daylight is an open source project that can be found on GitHub. And mydaylight.org is the instance hosted by my research organization, Saltese. And here's what it looks like. You'd have a multiple choice question. Students, here you have 5 answer choices that go with this thin lens question. And students not only have to tell you what they think the correct answer is, but they have to write an explanation or a rationale as to justify their choice. Now, on the second page, before revealing the correct answer, they're asked to reconsider. And the screen's here divided in 2. At the bottom of the page, what you see is that they have a subset of explanations written by previous students for another answer choice, D in this case. And then above it, you have explanations written by students who also chose A in the past. And so students have 3 options. They can change their answer choice, but to change their answer choice, they have to indicate what they think is the most convincing explanation. They could also keep the same answer choice, that's the second option, but indicate maybe a peer who did a better job of explaining it than they did, or they can keep their answer choice and stick to their own rationale, their own explanation. Now, when students choose a peer's explanation over their own, they're casting a vote for that peer explanation being in some way better than at least what was shown and what they wrote themselves. And this is important to us for 3 reasons. 1, it's a learning opportunity for students. It's almost a sort of feedback that they can get. By the votes that they accumulate, they're effectively learning what is a proper way to communicate their reasoning in their discipline. Teachers are getting a novel perspective as to what students think is convincing for their particular topic. And the platform benefits from this vote data in that it can be used to curate what good explanations are for future students. Now, comparative peer assessment is an extension of peer assessment that's been there for a while. Now, peer assessment classically has been, you give students a rubric and some peer work, and they have to provide a holistic score based on what's in that rubric. This is very difficult sometimes for students because they're still gaining expertise, so it's hard to evaluate their peers' content. And so comparative peer assessment, and there's multiple platforms now that are doing this, where students do provide feedback to their peers, but it's always after being presented in a pairwise comparison approach. They're given 2 peer submissions, and this feedback they provide is really in how one item is stronger or weakened in relation to the other. Examples include juxtapeer, here from University of California, San Diego, and compare from University of British Columbia. Now, in daylight, we believe that the votes that the students are casting are in a similar light, in the sense that students are saying that this rationale is more convincing, but only in respect to what they wrote themselves and what they were shown on at that time. Learner sourcing is also very much related to our work. Two very popular platforms out there, Peerwise from Auckland, and from our own colleague here at EDM, Hassan Khosrafi's Ripple, where students in both cases generate question items that will be done by other students as part of formative assessment and practice. But the important link with Daylight is that in both cases, the students have to also generate explanations for what is the correct answer choice that is then used by students who try that question in the future. Explanations data sets. So natural language explanations as data sets available for research. There are some in assessments where it'll be based on the hints that students generate in their skill builders. In DataShop, you'll have data from the Andes project, where people are writing self-explanations as they solve problems in physics. Kaggle recently hosted the automatic short answer grading competition. Short answers sometimes can get up to the length of a paragraph, which would be similar to an explanation in our case, in terms of natural language text that has to be automatically evaluated. But very similar and very recent is from the argument mining research community. IBM's Project Debater, they have released data sets of pairs of arguments on the same topic, labeled for which is more convincing. And we think that there's a real link there, and we believe that technology-mediated peer instruction data very much complements these data sets that are available. So our data set will have the standard, the fields will be the student, the question, their first answer choice, their second answer choice, what they wrote, what they chose as most convincing. You'll have the associated timestamps, but you'll also have what group, and we'll be talking about the groups a little bit because there is a teacher effect when you use a platform like this. How the teacher engages the students and uses the platform will have an impact on the data that's generated. We have 3 disciplines in our data set: physics, chemistry, and biology. Each item will have at least 10 responses. Each group will have at least 10 students, and each discipline will have at least 10,000 responses, as we said. And there's many contexts. Some teachers are using it as a pre-instruction, so it's a harder question. Sometimes it's post-instruction, pre-exam review, for credit, for bonus, optional. All of these things have an impact on the types of explanation students write. Now, just to get an idea of the size of the data, we're looking at about 100,000 student responses, half of which seem to be are in physics right now. But in terms of varying contexts, you can see in biology, we have really one freshman group that had 346 students in it. But each student on average answered 57 questions. So there's a longitudinal nature to the data that promises for future fruitful research. But in chemistry, you have an example here of 16 different groups. Some will be from different institutions that cover the topics. They share the content, the question items, but maybe the approach is a bit different. So there's going to be quite a bit of variability in the data. We have a visualization of the possible transitions that can be expected when you have 2 attempts at a question and there's a correct answer. What I want you to notice here is that students on their first attempt, 75% of them are getting it correct on their first attempt. So this is a data set of relatively easy questions. So that's the first thing to note. Second, the top band and the bottom band show the bias that students have in sticking to their own explanation. A blind, I think I have the best explanation. That's half the data, but the other half of the data is students really changing their explanation. And that's where the value, we think we are definitely certain that students are casting a vote there and choosing something else as more convincing, at least than what they wrote themselves. And there are 4 possible transitions. You could be going from the right answer to the right answer to the wrong answer, wrong answer to the right answer and then keeping the same wrong answer. What's interesting to note is that if you get it wrong on your first attempt, there's a 1 in 3 chance that your peer's explanation will bring you to the right answer. So I believe that speaks to the quality of the explanations in the data set, in the database. Challenges that lie ahead really lie in incentivizing students to write good explanations. You can see in some cases that in some disciplines, more than half of the explanations have less than 5 words. They can be keyboard smash. Because the teachers can't be reading all the explanations, the students know that. They figure that out. They don't necessarily put a lot of effort into their explanations, but that's not always the case, and that might not be the reason. We've led focus groups where students have reported that they didn't always see the value of writing a good explanation. So they would speed through the first step to get to their peers' explanations where they saw that they could learn something. So there's definitely work to be done there on the design of the platform. Also, teachers use the platform sometimes just to host their content, and it's not necessarily a rich conceptual question that demands much writing. It's a calculation. So those kinds of things have to be taken into account. It could explain some things. Another challenge is promoting students to actually take the time to read all of the text that's presented to them, which can be a lot. What we see here is on the right, you have 20% of the time students are choosing the longest explanation. So is that a blind reaction to the longest one must be the best? Is an important question to ask ourselves as we move forward. And what are the contexts where students reward brevity, where they're choosing explanations as convincing that are not the longest that are shown? And so these are avenues for future research. Also going forward is how do we extract insight for the data? This is a lot of text that's generated. How can we create interesting reports for students and for teachers so that they can benefit from the rich data that is being developed here? So I finished by this presentation with as an invitation. I'm part of the Saltese Research Network. This is a research practitioner partnership, and the platform that they support is called My Daylight, which is an open source project. But My Daylight is the hosted instance where you just have to go sign up, and we will facilitate you getting access to the data and collaborating for hopefully great collaborations in the future. Thank you very much for your time. I'll be happy to take your questions.